Welcome to the fastest way to learn data structures and algorithms with this premium revision material. Today we are mastering LeetCode 42. Trapping rainwater. This is one of the most famous hard-level problems, frequently asked in interviews at top tech giants like Google, Amazon, and Microsoft. Let us look at the problem statement. We are given an elevation map where each bar has a width of 1. Our task is to calculate how much water this map can trap after a heavy rain. Look at the visualization. The blue areas represent the trapped water between the black elevation bars. The key intuition is to think about a single bar at any index. How much water can it hold? It depends on its neighbors. Specifically, the amount of water a bar can trap is determined by the minimum of the tallest bars to its left and right, minus the height of the bar itself. If this value is positive, that is our trapped water for that specific slot. Imagine a mountain range with several valleys. If you pour water into a valley, it will rise until it reaches the height of the lowest peak on either side. If it goes any higher, it just spills over. This lowest peak rule is the secret to solving this problem efficiently. But wait, if we calculate the max left and max right for every single bar, we end up with an O of n squared solution or need O of n extra space. To achieve O of 1 space, we use our golden rule. The two-pointer convergence strategy. Instead of scanning everything repeatedly, we use two pointers starting from the ends and move toward each other, always processing the smaller side first. Now, let us dive into the dry run. This is the most important part. Look at the screen. We have our elevation map, and we initialize 2 pointers. Left at the start and right at the end. We also track left max and right max, both starting at 0. First, we compare the heights at our pointers. Height at left is 0, and height at right is 1. Since 0 is less than 1, we process the left side. Our left max is 0, so no water is trapped here. We move left to the next bar. Next, the height at left is 1. We update our left max to 1. Now, comparing left and right again, both are 1. We can pick either side. Let us move the right pointer. The height at the new right is 2, so we update right max to 2 and move right again. Now look at the middle. The pointer on the right is at a bar with height 0. Since our left max is 1 and right max is 2, the bottleneck is the left side. We calculate water as left max minus current height, which is 1 minus 0. Boom! 1 unit of water trapped. Notice the blue highlight appearing on the map. We continue this process, always moving the pointer with a smaller height and updating our boundaries. By the time the pointers meet in the middle, we have accounted for every single drop of water without any extra memory. Now that we have walked through the logic visually, let us see how this translates into our Python code. We define a function called trap that takes our height list. We initialize left max, and our result variable. While left is less than right, we check if height at left is less than height at right. If it is, we update left max using the max function and add the difference to our result. Then we increment left. If height at right is smaller or equal, we do the same for the right side, updating right max and adding to the result before decrementing right. Finally, we return the total water trapped. Looking at the complexity, the time complexity is O of n because we traverse the array exactly once. The space complexity is a perfect O of 1, as we only use a few variables regardless of the input size. And that is the trapping rainwater challenge mastered. Save this video for your next interview revision, and follow for more deep dive DSA explainers. Send this to your coding partner to help them level up.